Good morning. How are we doing? Did you go home with all kinds of existential dread following last Tuesday? No? You guys your generation was a generation that was born with built-in Wi-Fi and Bluetooth, so nothing amazes you anymore. What was it? My kids were the spoiled generation. And I was like, that's offensive. And the person telling me this said, no, not that like they're spoiled or you're spoiling them. It's just that they know who Luke's father is. They know who, Voldemort is. They know everything's been spoiled for them, right? In terms of like movies and shows and books and things like that. So it's like, oh yeah, that's about right. That just means we haven't moved on as a society from Star Wars yet. All right, what did we learn last Tuesday? We learned, probably above all, that time, number one, isn't what you think it is, because you really haven't thought about what time actually is. And number two, it's not the constant thing that our society seems to think it is, right? Like, we live and die by time, money is time, blah, 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 blah. But physicists come along and go, actually, time changes its duration depending on how fast things are moving. It's not a constant. And what we're going to do today is more examples of time dilation. We're going to learn about something called simultaneity, because if time is no longer constant, if time varies based on relative motion, then that means that the order that events happen also are not what we think they are. And then that's going to lead us into another issue, which is that if we keep the speed of light the same for all observers, then the natural result is time must vary and space, or what we think of as length, has to vary as well. So that's kind of where we're going to be going. And maybe, depending on how much I talk, maybe we'll actually get to some evidence today, right? Just to give you guys, your brain, something to go, okay, this isn't just like physicists being cute or creative, right? I'm not sure physicists would come up with this on our own. We are naturally lazy people and just want the universe to be a simple place, right? But this is the universe, believe it or not, at its most simple, even if it's hard for us to understand. Given any kind of relativity problem where people are moving relative to each other, what's the one thing that we can calculate 100%? But we don't calculate speed of light. Speed of light is just what it is, right? But in our toolbox, there's really only two equations, right? What's the one that requires no guessing and can just be solved? It's gamma, right? The gamma factor. Okay, the gamma factor is based on the relative speed between everybody in the problem. So let's go ahead and calculate the gamma factor. Okay, it's 1 over the square root of 1 minus v squared over c squared. And in this case, that's 0.65 squared. Where'd all the c squareds go? They just cancel out, right? I don't even bother to write them in and cancel them out because I'm old and jaded and I've done this too much. I think this is 1.316. And again, what are the units? It has no unit. It's a factor that tells us how much relativity is affecting the perception or measurements of time and space and everything else. Okay, so we got gamma, right? Low-hanging fruit, pretty easy to get. What are we doing? Okay. What is the thing that is being measured in this problem? Heart rate. Heart rate is being measured. Okay. The problem with all relativity problems is that you are forced to really think in detail what it means to measure something. What's being measured? How is it being measured? And especially when it comes to the time interval, how is the time interval being measured? So let's talk very specifically about how you would measure someone's heart rate. Okay? So if you've ever been to the doctor's office, what do they do to measure your heart rate? Yeah, they hook you up to a machine, right? Okay? It used to be that you could do pulse on the wrist. You still can. Up here is a little bit better if you want to tell if they're living or dead. But you hook you up to either there's a little thing that goes on your finger that gives the oxygen in your blood, but it also can tell the heart rate. The blood pressure cuff can also sort of a secondary way of finding out the heart rate. So the computer does it, right? But what does it mean to measure a heart rate? What are the units that are given in this problem? It's a beat per minute, isn't it? So what's the time interval? It's 1 minute. And now we have to try, the hard part about any relativity problem is figuring out what's proper. And in the case of time measurements, we have a definition for what proper time means. Does anybody remember what the definition of proper time is? Is it like very British time because people are proper? Or is it something else? Yeah.
The one who's stationary to the event being observed.
Okay. I'm glad Caleb said that. Okay, because the shortcut your brain wants to make is to say the thing that's not moving. I promise you that is going to get you in trouble. Okay? Unless you are exceedingly careful, right? The thing that's not moving is going to get you in trouble. Because the thing that's not moving is a matter of interpretation depending on what frame of reference we are talking about. What are the two frames of reference in this problem? There's got to be two actors or two people watching something. Who are the two groups of people? The astronaut and the people on Earth. So here comes Mr. Balogh's crude. This is like the one I draw for every relativity problem. The surfing carrot astronaut and the people down on Earth, right? So those are our two observers, right? And we have a measurement of 55 beats per minute, or a time measurement that's taking 1 minute to do, right? And they just count the number of beats, that sort of thing, okay? So who measures the 55 beats per minute? Nope. You want to guess again? Nope. When the astronaut measures her heart rate, sorry, you were absolutely correct. I was reading wrong. I'm so sorry. That was my fault. Earth sees the 55. I was doing a different problem. Earth measures 55 beats per minute. So Earth is reporting the 1 minute time interval. Does Earth measure dilated or proper time? Why did you say dilated? Because you're guessing and 50-50 and maybe? No, what was your thought process?
From the last problem, it was because the time on Earth was longer than... Okay, so you're kind of falling back on what we did last time, but I could be trying to trick you now, right? Because in the last one, the person doing the measuring was on the spaceship, weren't they? That calendar, that 1 year calendar on the ship's clock and calendars, right? Try to put yourself into both frames of reference. So what does the Earth see? They see the astronaut moving past, right? But what does the astronaut see? Them, the Earth, moving the opposite direction, right? Relativity, and actually all of the laws of physics, they work regardless of the frame of reference that you choose, okay? What I mean by that is both of these frames of reference are correct. It's not like
one is more correct than the other. They are both equally valid ways of applying the laws of physics and doing observations. Okay? And remember, the people in each of these frames understand this. They're not being stupid. They're not measuring the wrong things. The difference in time measurement is a real, measurable thing that happens in our universe when things go fast. So, in these two frames of reference, only one of them can be recording a time that happens at the same place. Think about what is being measured. What's being measured? A heart rate. What is the only frame of reference where the measurement of that heart rate happens at the same place? Is it this frame of reference? Frame number 1. Or is it this reference? Frame number 2. I always feel like a game show host. Behind door number 1, door number 2. Door number 2? Why is it door number 2? A heart rate better be at rest with the patient whose heart it is. Because if the heart is moving relative to the patient, that's an issue. Right? Right? So for people in the lab, what are they seeing? When they start their 1-minute timer, where's the heart? Somewhere there, right? Okay? And then when they stop their 1-minute timer, where's the heart? It's over there. What we are talking about are the events, right? A beating heart, the beginning of a 1-minute time interval, right? The people on Earth measure the 1-minute time interval, but the events that they are using to start and stop their observations are based on something that happens in one place, and then after the time interval goes by, it's in a different place. But the astronaut, with her stopwatch, right, measuring her pulse rate, when she starts her stopwatch and stops her stopwatch, has the thing she's measured moved? No. So Caleb's idea there about something that's stationary, right, or not moving. The reason that's a bit of a trap is because you can look at it from two different frames of reference and argue yourself into, well, this isn't moving. It's very common. The mistake people make is, oh, well, the Earth has got proper time because they have the stopwatch. It's not moving. So, no. The stopwatch is just a measurement device. The events that are being observed, right? That's what matters, right? On Earth, they measure a time interval between events that, from their frame of reference, happen in two different locations. But when the astronaut measures the same events, the beating of the heart, that's happening at the same place. Because for the astronaut, the Earth is going away and they're standing still. It's a subtle yet crucial difference in what we mean by the events for the time interval happening at the same location in space. It requires careful thought and analysis, and as noobs doing this, you can argue it both ways and both seem legit. So how do you learn to argue the correct way? Practice, 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 practice. When it comes to this stuff, for the last week, I've been practicing just to bring my brain back up to speed, right? This is not something I can just whip out of my back pocket and do. Optics, I can do that. This stuff, no way. So, after all of that, what is Earth measured? Proper or dilated time? This 1 minute is dilated time. And the reason it's dilated time, leave yourself a note. right? It's going to really help you in your analysis when you go back and you got it all wrong and you got to flip your definitions and you're like, why did I make this mistake, right? Dilated time because heart rate in two places, right? Just a note to self, right? This is what I was thinking at the time. Makes the failure analysis easier to do, and it makes the patting on your back feel so much better when you can point at it. See, I did it right the first time. Okay. So, we're trying to figure out what the astronaut measures, right? If 1 minute's the dilated time, and the only equation we have, right, is dilated time equals gamma times proper time, what are we solving for? Proper time. We're solving for the astronaut, right? The hard part is figuring out what the, is it dilated, is it proper? After that, the math is easy. So we're going to take the 1 minute, we're going to divide by 1.316, okay? And did I do that? I got 0.76 minutes. Okay. What has to be the same in the observation? If time is changing, what's the other thing that kind of has to be the same? The number of beats, right? Like we can measure a different heart rate, but the thing that was counted was 55 of them, right? So to calculate the astronaut's heart rate, it was 55 beats in, was it 1 minute? No, 0.76 minutes. So the astronaut's heart rate turns out to be 72 beats per minute. As an aside that has absolutely nothing to do with this lecture, I always scare the nurses when I go into the doctor. Not because I want to, but because I sit down and my blood pressure is 130/80, because I'm old, and my resting heart rate is 48. No, that is a sign right there that there's something very wrong in a normal individual. Depends. It doesn't depend. If I walked into the ER with that, they'd instantly be hooking me up to things. Okay. But what I have to tell the nurses every single time is that no, that's normal, because back in like high school, my resting heart rate was 45. Like for whatever reason, my resting heart rate's always been low. And I used to have a low blood pressure to go with it, but the pumps and the pipes are all getting older. All right, so that's what the astronaut measured. We did all of that, right, from the point of view of measuring the 1 minute. But gamma, the gamma factor, the dilation factor, affects all systems equally. And so we could have just done 55 beats per minute, okay, times gamma, and gotten the answer. Right, it's an inverse minute, okay? And so we know that the heart rate for the astronaut has to be higher because the people on Earth measured a dilated set of events, right? Means that the time interval stretched out between heartbeats. And so, what's 55 times 1.36? Well, it turns out to be 72. Right? So like the safe way is to always go to the time interval, but like I wanted to just kind of show you that gamma affects everything. It affects heart rate, affects growth rate, affects cellular metabolism, everything that depends on time and space is affected by relative motion. Okay, I would like you right now, with each other, the people next to you, I want you to have an argument. I don't necessarily want you to solve the problem. What I want you to decide is who's measuring proper time and who's measuring dilated time. Okay? You have the astronaut, you have the lab people talk about what's being measured, who's doing the measuring, and who can see those measurements happen at the same place. I'll give you 2 minutes. Go.
To be honest.
So, in the beginning, he made us like do that.
But no shot.
Yeah.
Since I missed the first question, I'm kind of confused at what this is.
You actually don't even really need the first question. So, 2 sets of observers, people on Earth in the lab and the astronaut, right? Figure out who is measuring proper time. Again, there's another 1 minute interval of time, right? They're measuring 60 beats in 1 minute. But who has the proper time measurement? All right. How many of you guys talked in circles? Like you started at one opinion and then changed your opinion and then came back? Yeah? Happens all the time. Happens all the time. Okay? What are you going to need to be able to do this homework? Like really do it. And I'm not saying ChatGPT. You need another brain. Not just your brain. But you need another brain. Why do you need another brain? And by that I mean another person. To talk it out, right? To really try to argue from both sides. As being new to relativity, this is nearly impossible to do on your own. As you get into it and you start realizing all the different frames of reference and all that kind of stuff, you get to a point, like I can sit there and argue both sides. But that's why people think I'm crazy when I sit in my office and I talk to myself, right? It's like I'm trying to argue both sides, seeing it from both frames of reference, all that kind of stuff. It's very hard to do. So more so than any other place in physics, you really need somebody else to just argue about like the issues in the problem with, okay? Do it over Discord. Do it in study groups. Come to Grasp, right? Argue with me, whatever. But you really need that external from you sort of ideas and feedback to really get a handle on proper time. I have noticed ChatGPT gets this wrong roughly 50% of the time. Remember, AIs don't reason, right? They give statistical connection between words, okay? So statistically, proper time, dilated time, it's all happening with the same, chance as any other thing. And so basically ChatGPT just guesses. Like it really doesn't know. I haven't tried it in the last 2 months. But one of my tests of AI is magnetic fields, and the other one is relativity. Like I watch it mess up more often than not on these concepts, right? Depending on how well the AI is connected. Like when ChatGPT is connected to Wolfram Alpha, it does way better, right? Because it's not, in that sense, it's just a chat interface for Wolfram Alpha, which Wolfram Alpha is able to nail it more often than not. So anyway, just realize that ChatGPT will argue it one way, and then the very next same prompt, new discussion, will argue it the opposite way. Because again, it's guessing on the word association. All right. What's being measured? A heart rate. A 60 beat per minute, or beats per minute. So it's a 1 minute time interval. And who measured the proper time? Why'd you say the lab people? The events of starting and stopping the heart rate are in the same location, namely the lab, for the lab observers. The astronaut, on the other hand, what's the astronaut going to see? The astronaut, in her frame of reference, assumes she's standing still and that the Earth is going somewhere. So she's looking at measuring a person in the lab's heart rate. She's going to start her stopwatch and see the person here, and then when she stops her stopwatch, she'll see the person there, right? Two different locations of the things she is measuring. Okay, so we're going to assume that Earth has proper time, heart rate, same place for lab people. For people in the lab. They're not lab people, they're people in the lab. So that's 1.316 times 1 minute. So that means that 1.316 minutes went by. And for the astronaut, 60 beats in 1.316 minutes equals a 45 point, we'll call it 46 beats per minute is what the astronaut would measure. Is the math difficult? No. Is the concept brain melty? Yes. It can really my advice, this is stupid advice. My advice is to accept it. Just accept it, embrace it, let it flow through you. Try not to fight it. I know your brain wants to go, well, this is dumb. When am I ever going to use this stuff? Those are all valid arguments. Well, not that it's dumb. It's actually pretty smart. But accepting it will take the friction away from your brain, right? Trying to figure out just what the heck's going on. Yes.
So 46 is what the astronaut's observing.
Yep.
So they're thinking time is going slower.
For the people on Earth, yes. But what do the people on Earth say about the astronaut? They see the astronaut's time frame moving slower. Yes. Karen, seeing you drive by, says that your clock is running slower. But you, standing there watching Karen go by, say that her clock runs slower. Who's right? Both.
So on the previous equation,
Yeah.
the heart rate increased from one of the previous, right? But then this one we just did, it decreased.
Yeah, you don't want to look at whether it's increasing or decreasing or that kind of stuff, right? Okay. Because these are different problems measuring different events. Okay. The people on Earth watched something go by and measured a heart rate. Okay. But now They've measured different things. Now they're looking at some other events that are taking place in their frame. No, can't do that. This is not a mirror image or anything.
When you gave the initial speed as 0.65 c,
Hmm.
do we know how quickly Earth is moving relative to the speed of light?
Really slow.
Slower than 65 c?
Oh, it's like 0.01 c.
Okay.
Like it's really small.
So the astronaut speed is closer to the speed of light than is Earth's.
Oh, way close. Yes. Earth doesn't move very fast at all around the sun.
And then the sun might be moving?
Oh, the sun's definitely moving. But moving with respect to what? Because there's a frame of reference where the Earth isn't moving at all and the rest of the universe is going around it.
Right.
We haven't done general relativity yet. All right. Time. Time isn't what we think it is. Time isn't a constant. The measurement of time depends not only on how fast something is going, but what's being measured. And so this has knock-on effects. The dominoes are starting to fall, and one of the dominoes that's going to fall is this thing called simultaneity. What does it mean for something to be simultaneous? Two things happening at the same time, right? Now, in our universe for particles, that generally means that there were two events that happened at the same time, but not at the same place. We could have simultaneous events where one of you walks through that door and one of you walks through that door. What's the same between the events? The time, right? But is the location the same? Not necessarily, right? So simultaneity is this big fancy word that references an idea that if time and the perception of time is now different for different observers in different places and different frames of reference, then things that look simultaneous in one frame are not necessarily simultaneous in another. Let's watch a video. An animation that hopefully will make something that is very non-intuitive a little less confusing. It would really help if the sound input stayed the way it's supposed to be.
Consider two observers in relative motion. In this case, Albert and Henry, just for the sake of argument. At the exact place and time they pass each other, they observe a flash of light. A sphere of light expands outward from that point. Since each measures the speed of light relative to himself, each believes correctly that he is always at the center of that expanding sphere, even though they themselves move farther and farther apart. How can two people in different places both be at the center of the same sphere? To confirm his perception, each sets up light detectors an equal distance apart. However, while Albert's detectors register the light arriving simultaneously, he believes the light strikes Henry's detectors at two different times. Meanwhile, Henry sees the same thing in reverse. They agree on the speed of light. But they disagree on whether events happen simultaneously or at different times. This is not semantics, nor a petty debate. It means that time, as well as distance, has to be affected by motion.
Does anybody want to leave now? Ha, it's too late. We're past the 9-week deadline. All right, what the heck is going on here? We're gonna play this video again, okay? And I'm gonna pause it a lot because we've got to talk about like the statements that the narrator is making, right? Because some of these statements are like, "What the heck you on, man?" Okay, so let's see what's going on here. This is on YouTube. It's called The Mechanical Universe and Beyond. Don't ask me which of the 56 episodes this is in. I can't remember anymore. Okay, Albert and Henry. Who's Albert? Einstein. Henry is Heinrich Lorentz. Heinrich Lorentz was a mathematician who developed like the mathematics of relativity. He did something called the Lorentz transformation that we're not going to learn, but is the basis for the mathematics of relativity. And what Henry was trying to do was disprove relativity, but he pulled a Poisson, is what happened, right? He ended up developing exactly the math that we needed to make it. Henry was trying to save ether theory by showing that there was a shift in anyway, that's history. It's just, the point is, Albert and Henry are on two different sides of a coin, talking about relativity.
Consider two observers in relative motion. In this case, Albert and Henry, just for the sake of argument.
Because they argued. Scientific argument.
At the exact place and time they pass each other, they observe a flash of light.
Okay, so what's the condition for what they're observing? At exactly the same place and time. And I know it looks like in the video that they are in two different places, but what we're talking about here is their x coordinate. Don't worry about y and z, okay? Because they end up not mattering, okay? So at the exact like horizontal position and time, what happens? A light flashes. Okay? And we see the expanding sphere of that light flash because light goes out in all directions. And what speed does it go? The speed of light, according to who? Everybody. Remember, special relativity requires that the speed of light be the same for all observers regardless of relative motion. If we hold on to that fact, and it is a fact, I'll prove it later, then we have to allow for time to be different. And as I've already alluded to, space as being different as well.
A sphere of light expands outward from that point. Since each measures the speed of light relative to himself, each believes correctly that he is always at the center of that expanding sphere.
Each of them believes correctly. Nobody's getting duped here. This isn't CGI, right? It's not that one of them is mistaken and the other is correct. That's what our brains want to believe because we've grown up in a society, in a world where there is one right answer, right? But like, these are equally valid, true statements. They are both at the center of the same exact sphere of expanding light. Even though they're moving relative. My brain broke. What? No, come back here. That was stupid. Misclick.
Sphere of light expands outward from that point.
Sorry.
That he is always at the center of that expanding sphere. Even though they themselves move farther and farther apart. How can two people in different places both be at the center of the same sphere?
So that's like the crux of the issue, right? They're in different places, but they're both at the center of the same expanding sphere of light. This is where my brain gives up. Like, honestly, I'm just like, okay, fine. Whatever. Whatever you say, dude.
To confirm his perception,
What do they do? To confirm their measurements, their perceptions, what do? Experiment. This is science, right? This isn't philosophy class. We need to do experiments to verify what we're measuring and what we are perceiving. So that's exactly what they do.
each sets up light detectors an equal distance apart.
What is the experiment based on? No. Light. The one thing that they can both agree on, right? The one thing that is the same, regardless of what frame of reference you are in, the speed of light, okay? Like our light clock, right? It's based on the one thing that can be the same for all frames of reference. I like Henry's noise
However,
better.
While Albert's detectors register the light arriving simultaneously, he believes the light strikes Henry's detectors at two different times.
So why does Albert say that his detectors are simultaneous? He's at the center. The two detectors are the same distance away on either side, right? The light flash started here, and it goes equal speed in all directions, so there's no choice. Both of his detectors will go off at the same time because they're both the same distance away. Speed of light, distance away, basic physics, they got to happen at the same time. But he sees Henry's detectors going off at two different times. Why? Why does the detector at the back of Henry's train car there go off first? He's moving, right? Like the light pulse is moving backwards, but Henry is moving towards it, right? In other words, the distance that the backwards light pulse has to go is much shorter than like the light having to catch up with the detector on the front of the train car, right? Again, standard basic physics. The laws of physics are the same in all frames of reference as long as they are non-accelerated. So, this is what Albert measures. His experimental apparatus is telling him that his are simultaneous and Henry's happen at two different times.
Meanwhile, Henry sees the same thing in reverse.
Okay, same thing. What did Henry see? Because he didn't see the same thing. What did Henry measure? That his detectors do what? Go off at the same time. But Albert's are different for exactly the same physics and reasons that we just talked about that Albert said, right? Okay? So here we have true, honest, physical experimental measurements giving different results based on the frame of reference being different and the relative motion between those frames. Because what's the only way that the two experiments would completely agree and be exactly the same? In order for Albert and Henry's detectors to go off at the same time, they have to be at the same place and not moving relative to each other.
They agree on the speed of light,
Yay!
but they disagree on whether events happen simultaneously or at different times. This is not semantics, nor a petty debate. It means that time, as well as distance, has to be affected by motion.
This is not semantics, nor a petty debate. Let's break that down. What does the word petty mean? It usually means unimportant, okay? Or to be petty means that you are acting in a way that really isn't helping, right? You're not forwarding a cause or helping anything out. You're just kind of, you're not necessarily being productive, but like you're not trying to help, but you're also trying to slow things down. That's kind of what petty means, unimportant. This is not semantics nor a petty debate. So petty, this is not an unimportant debate. Like there's something crucial going on here, right? Semantics. Does anybody know what semantics is? It's like language. It's word choice in language. Semantics is what words you choose to express yourself, right? And the words that you choose can have very different meanings depending on the context, the situation, all that kind of stuff, right? So semantics is word choice. So this is not just a different choice of words, nor an unimportant problem. This is real. This happens. So what are the implications? Yes?
So when we see light from Albert's perspective, it's traveling equidistant from where the light went off.
Uh-huh.
And then
Uh-huh.
the gentleman up top, Henry,
Uh-huh.
he's moving.
Uh-huh.
Where the light went off is different from where he is.
According to Albert.
So
But in Henry's frame of reference, where's Henry?
where the light went off,
Uh-huh.
but he's moving.
No. In Henry's frame of reference, Albert is moving.
Right.
This is really bad. Sim's right on she's there, right? Okay? And the more you're there, the more you realize you have no idea what's going on. Right? Like you're just like, yeah, yeah. Why do I do this to people? One of the reasons I do this to you, I guess one of the reasons is that the state of California demands it. Number two, that it's part of the curriculum. But the real reason is because this is truth. This is fact. This is correct. The lie that we told you in Physics 2A that time's always the same no matter what you're shooting or where you're going, it's a total lie. It's a good one. It makes doing kinematics much easier, right? But it's really not true. This is gloves off, Mr. Balogh. From starting with relativity all the way to the end of this course, I'm not going to lie to you anymore. I'll lie a little bit, right? But like, we're not pretending anymore. We're not going wink, wink, right? Just friction. No, we're now telling you the way the universe works, and we got to deal with it. Yeah.
So I don't know if it matters or not, but with the light that they see, is that a light that's going like outwards, or is it a light that's coming inwards, or does it
Yes, light does all those things. If I show you my cell phone screen, right, the light goes from the screen to you, but it also goes out this way because Evan was able to, right, all these different, right? Okay, so yeah, light spreads out as a wave in spherical pattern all around. Oh no, the medium matters. We just spent the last 3 weeks. And these guys are all in the same medium. Yeah, vacuum, air, doesn't matter. All right. So this is not a semantics nor a petty debate. What it means is that time as well as distance must be affected by relative motion. Simultaneity teaches us that not only does time change based on relative motion, but our measurement of distance as well. So we're going to tackle that next. Now that my iPad has gone to sleep because I talk too much. Okay. Important talking. We had time dilation, the spreading out of a time interval, and now we're going to talk about length contraction. This is the yin to times yang. Okay? If nothing else, Albert Einstein taught us that space and time are not separate entities. They are very much connected to each other. You don't live in a three-dimensional universe, you live in a four-dimensional universe. That fourth dimension of time is very, very important because, again, you woke up this morning thinking that time is independent of where you are. And what I'm now teaching you is that is not the case. Time is very much dependent on position, and position is very much dependent on time. They affect each other. So, under length contraction, this thankfully is way more straightforward than time. And the reason that it's more straightforward than time is because we're used to measuring the lengths of things and being taught properly how to measure the lengths of things. Before we get to the concept, let's just do the equation. Gamma's back, right? L naught, you want to guess what that is? Proper length, right? Okay. And then L would be the contracted length. And the reason it's contracted is because gamma is a number that's always bigger than 1, and we're dividing a length by a number bigger than 1, and anything you divide by a number bigger than 1 gets bigger or smaller? Smaller. That's why we call it contracted length. Okay. What is this? This is a meter, right? It's a meter stick, but it's also a meter. Why is it a meter? Because we say so. Okay? Just like we say a second is... I forgot to go look it up, how many vibrations of a cesium atom, right? Okay? So like, at its base, any measurement is because we say so, right? But what we're talking about now is what do the measurements look like as they move, right? And quite frankly, I wouldn't blame you for, accusing me of being on something if I say that this meter stick changes its length because I'm walking along the front of the room. I mean, it's crazy talk, right? Is this meter still a meter if I walk versus when I stand still? Yeah. But now if I throw it at the speed of light or very close to the speed of light, it's not going to be. In fact, what will it look like? If the length contracts, what will it be? Longer or shorter than a meter? Shorter than a meter. Things that move at close to the speed of light are observed to not only have time run slower for them, but to have their lengths squished. So, a spaceship flying by at near the speed of light, what would that look like? Like if the spaceship looks like the standard carrot when it's sitting still, right? But then we send it at very fast speed of light, what would it look like? Contracted, but contracted only in the direction of motion. Remember I said how y and z don't matter? No matter what direction something's going, you can always define a coordinate system that makes it a one-dimensional velocity, right? So all the contraction takes place only along the dimension of travel. Usually spaceships go forward, right? So this spaceship would look like this. Right? It's got the same, I kind of made it the same. Not really. Anyway, you get the idea, right? Same height, but, right? So, how do I lose weight? Orient my stomach front to back in the direction of motion and go really fast. Because then what will it look like? I'll look thinner. Okay? I'll look the same height. Okay? Can I get taller? No, it's contraction. So, but I can look thinner, right? Extreme weight loss tactics. Go to the speed of light. Which actually doesn't work because we'll talk about something else later about mass. Anyway, so length contraction. Proper length. We should define proper length. Oh my gosh, Mr. Balogh going to give some definition that I'm still not going to understand. No, this one's much better. Proper length is the length that is measured at rest. Full stop, done. When is a meter a meter? When it's at rest. When you're looking at the meter stick and it's not moving relative to you. When does the meter stick get shorter? When it's moving. Okay? So, Sim and Truman in their car, what did Karen see? A squished up car, right? Okay. What did Sim and Truman see? Karen standing on the road? Squished up Karen. Okay. Yeah?
Random question. Can you argue that we are going at the speed of light and light
is like these are fantastic questions. And the reason I wanted to slay you alive was I could get really down the rabbit hole. Okay? So okay. Spoiler alert, we're going to talk about something we're going to talk about on Tuesday. Okay?
What Tuesday's better?
Thursday. Monday. I don't know. What are we doing on Monday? Oh, Monday we're doing practice, I think. I think we're practicing relativity problems on Monday. I think it might say lecture on the schedule, but you're right. Veterans Day is Tuesday, isn't it? I'm really evil for making you guys come on the Monday. Only have Tuesday, but I can't do anything about it, I don't think. I mean, I could take a sick day. But I'm not sick, so. I'm not going to lie. I've already used up my 2. We have these things called gone fishing days. It's not a part of HR. HR doesn't know about it. But basically, our dean says, 2 of your days per, semester, we don't ask why.
Like doctor appointments or something.
Whatever. We just don't ask why. But I've already used up my 2 gone fishing days because of doctor's visits. So nobody make me sick. We will meet on Monday, and then Tuesday is off. Okay, so we sorted that out. I'm trying to avoid Caleb's question because it is such a good one, and it's going to take us places we really can't go right now. But here's something that you need to realize about the speed of light. Okay, we can't go the speed of light because the only things that can go the speed of light have no mass. Mass is a big problem. So far we've talked about time and distance, but everything changes if you insist that the speed of light is the speed of light. Time, distance, force, mass, acceleration. These all have to be redefined. General relativity will talk about mass, acceleration, and force. Okay? So number 1, we can't go to the speed of light. But what does the universe look like for a photon? Since Caleb really asked that question. Very compact, because from the photon's frame of reference, it's not moving, and the rest of the universe is, right? Relativity. But what is the amount of length contraction observed by a photon that, by definition, is moving at the speed of light? How much is the contraction? What is gamma for the speed of light? It is infinite, right? Okay? And so What does infinitely contracted length look like?
9.
0 length.
Oh my god.
So for a photon, the universe has no XYZ anything. For a photon, the universe is a infinitesimally small point. How much time does the photon perceive? No, we are nowhere near string theory. String theory is all about drugs. We'll get to that later.
Say the question again?
If the universe is infinitely contracted for a photon, what's happening to its time?
Being stretched?
Infinitely dilated. So for photons, there is no time. There's no time interval. The interval between two events is infinitely large. So time doesn't exist for photons. And the universe is an impossibly small place. This gives rise to the joke that nobody seems to get, right? Because no joke is funny when you have to explain it, right? Right? Why is the life of a photon boring? Because they have no place to go and all the time in the universe to do it. You going to use that one? Your social credibility will drop. So, they're fantastic questions. And this really is the greatest benefit of talking about relativity, right? So we start talking about these universal truths, they start creativity and flights of fancy and what ifs and how does it look. And you are tapping into that same human drive that Einstein had to really imagine things beyond our capability to even see right now. It's a wonderful part of our humanity. Okay, so let's run a length contraction problem. That was a picture. And what we're going to do is we are going to show you one of the first pieces of evidence. This is going to be a video clip from something that happened in the 1940s and 50s. It's like even before, this is older than Mr. Balogh. Craziness. All right. Stop. Okay. So just to preface this, we're going to do a length contraction problem, but we're going to do it with a certain cosmic ray particle, a particle that's produced when cosmic rays interact with the Earth's atmosphere. They're called mu mesons. You can think of them as like super heavy electrons. It's not too far off, slight lie, but good enough. Okay? So they're going to set up an experiment that we are going to then do calculations that are based on this experiment.
A quarter of a century ago, Dr. David Frisch of MIT
More than a quarter.
and Dr. James Smith of the University of Illinois
2 quarters.
filmed a classic experiment proving the reality of the relativistic time dilation. They did it by measuring the flux through the atmosphere of a radioactive subatomic particle called the mu meson. Created at the top of the Earth's atmosphere by cosmic rays from outer space, mu meson zooms straight downward at nearly the speed of light. But laboratory experiments, such as the one done here by Smith, show that mu mesons disintegrate naturally after an average life of only 2 millionths of a second. That means that even going at near the speed of light, they shouldn't make it very far through the atmosphere before decaying. Or to put it differently, when Frisch and Smith observed 568 mu mesons in their detector at the top of Mount Washington, they calculate that only 27 per hour ought to make it to the base of the mountain. But when they cart their equipment down to sea level, they find almost as many mu mesons as they had at the top, 412 per hour. Of course, Frisch and Smith really aren't a bit surprised. The reason for the discrepancy is spelled out by the theory of relativity. Traveling at nearly the speed of light, the mu meson's internal clock runs slow so that, as viewed from Earth, they take much longer on the average than 2 millionths of a second to disintegrate. Or, to put it differently, as viewed from the frame of reference of the mu meson, the Earth's atmosphere, rushing upward at nearly the speed of light, is Lorentz contracted to such a degree that the particle can easily make it all the way to the ground in only 2 millionths of a second.
Okay. An experiment is devised to measure the number of mu mesons per hour at the top of a mountain and the bottom of the mountain. Classically, the prediction is that at the top of the mountain there should be more, and at the base of the mountain there should be less, because mu mesons have a very short lifetime. They're created and destroyed in 2.2 millionths of a second, or 2.2 times 10 minus 6 seconds. On average, the mu meson is moving at 99.5% the speed of light, which is a gamma factor that's close enough to 10 that we're not going to use any of the decimals. Okay? So the experiment, though, reports that when the detector is moved to sea level, there is almost as many mu mesons as there was before. Right? So what we're going to do is we're going to explain, using relativity, the discrepancy between classical theory and what is actually observed in the lab, or in this case, on the mountains. Okay, so we know the speed, we know the gamma factor, and we know how long the mu mesons live. They're not alive, but how long they exist, right? In the lab. Okay, it's called the rest frame time. Okay, so we're going to say that the distance here is 5 kilometers from the top to the bottom of the mountain. Okay, and we are going to we'll do length contraction first, and then we'll do time dilation. Okay, because we're talking about length contraction right now. Okay. So if we're going to use length contraction to try to explain the discrepancy here, right? What do we know? Well, there has to be a length, a contracted length, and a proper length. What are the two frames of reference that we are comparing or referring to? Who are the observers? We observe the particle. So scientists observe the particles, right? And then what's the other frame of reference? The particles observing us, or at least the particles frame. Because from our point of view, we watch this particle get created and then get destroyed, right? But from the particle's point of view, it's standing still and it's seeing the Earth rush up at it, right? Those are the two frames of reference. I've drawn the frame of reference of us, right? Standing here looking at what's going on. So the 5 kilometers, that's our distance. Proper or contracted length? This is proper length. Why is this proper length? The mountain is not moving relative to us. Right? Is the mountain moving relative to the mu meson? Yes, right? Because the mu meson's created at the top of the atmosphere, and it sees the mountain moving towards it, right? Okay. So the proper length must be 5 kilometers or 5,000 meters, right? So the contracted length, or the length that the mu meson sees for the top to the bottom of the mountain, is going to be 5 kilometers divided by gamma, which is about 500 meters. So for the mu meson, the mountain is not 5 kilometers tall. It's 500 meters tall. Okay? And how far can the mu meson travel in its lifetime? Well, that's basic standard physics. How fast is it going? How long can it do it? Put in 3 times 10 to the 8 for C, and you'll get 656.7 meters. So the mu meson is capable of traveling a distance in its frame of reference of 656.7 meters. But for the mu meson, the mountain is only 500 meters tall. So can it make it from top to bottom? Yeah, with 150 meters to spare. You cannot explain the experimental evidence through classical physics alone. You must make the correction for length contraction. Let's do it from the point of view of time dilation. All right. In time dilation, who's measuring proper time? Now, the time we have is the 2.2 times 10 to the minus 6 seconds, as measured in the lab. So, do we measure proper time, or does the mu meson measure proper time? It's the mu meson. Just because we measure it in the lab, right, doesn't necessarily mean anything. Because as far as the mu meson is concerned, it's the only thing that can measure two events happening at the same place. Because for the mu meson, the rest of the universe is moving around it, right? So it turns out that our proper time is... Oh, no, sorry. Let's back up. Let's do a different calculation first. Distance equals velocity times time, right? Okay. So the time to go 5,000 meters, 5 kilometers, at 0.995 C is 16.8 times 10 to the minus 6 seconds, right? So the classical physics calculation says that you need about 17 microseconds for a mu meson to be able to go the 5 kilometers. This is ignoring length contraction, right? So we say, well, 2.2 is less than 17, so it's not going to work, right? But as far as we are concerned, here in the lab, watching the mu meson travel, are we measuring dilated or proper time? We're measuring dilated time. We see the mu meson at the top of the mountain, we see it at the bottom of the mountain, right? That's two different places, right? So when we measure that dilated time, like what is our dilated time? Well, the proper time is the 2.2 times 10 to the minus 6 seconds. So we take 10 times 2.2 times 10 to the minus 6 gets us 22 times 10 to the minus 6 seconds. So as we measure the mu meson moving at 99.5% the speed of light, we look at it and go, well, its lifetime isn't 2.2. That's its lifetime when it's just sitting still. But now that it's moving, its lifetime is much longer, and long enough to be able to get from the top of the mountain to the bottom. Mu mesons and their journeys through our atmosphere cannot be explained using classical physics alone. The results of the experiment can only be correlated with the theory by incorporating relativistic effects. We see this all the time, and not just with mu mesons. Subatomic particles, electrons, protons, neutrons in particle colliders routinely behave as though their lifetimes are longer than they actually are. That is a measured, observed phenomenon that happens on a daily basis in labs around the world. when we come back together on next Thursday, because Tuesday's a holiday, we are going to move into more implications. The dominoes continue to fall. And we might start general relativity, where we're going to start talking about what happens when we allow for accelerations and forces and all that kind of stuff. Okay? So a lot more yet to go, but I think you can do at least half of your homework now with time dilation and length contraction. We'll cover relativistic velocity addition and some of the other parts next week. See you hopefully in GRASP, but I'll see you on Monday for lab.